vectors, is it? I guess. Alright, so same things to note as yesterday, except I managed to get the quiz number right. So today we're going to look at SQL and start on to stored procedures, which is a way of extending the capabilities of SQL. Right, here's another famous database nerd. Anyone know? Don't say Dumbledore, because it's not. It's another one of these system art people. So it's Bruce Lindsay, also from IBM, worked on the initial prototype relational database system R. He built the buffer pool manager, which is extremely important in databases. They rely heavily on lots of memory buffering. And since then he's worked on a whole bunch of other stuff. And he's an IBM research fellow. Okay. Well, no, I didn't do that. I want to do this. And I forgot to bring my mouse, which is annoying. Alright, so what were we up to? Oh yeah. Well, so a couple of things you can do with SQL that are a little bit unusual, and most DBMSs will support something like this, but occasionally if you've got null values, you don't want them to appear as just empty null values. You might want to actually make something appear on the in the output. So let's, by the way, I've almost got to the point where I can probably do exercise 2. So I think I've set things up so that if you run the script, something I didn't mention yesterday, actually, no, I don't want to. Alright, I've got a Postgres server running, I think. Yes, I do. So the way the script is going to work, if you're using Greek, then you need to run this pg-init script once and it just sets things up for you. If you're using anything else, you need to run the pg-init script each time you log in. Anyway, exercise 2 will describe all of that. Okay, so what I've got here is a database about students, and there's a single table of enrollments, and I set it up. So let's just have a look. So it contains student names, course that they're doing, student numbers, course that they're doing, and their mark. So you can see that, as usual, Richard gets his marks in late. So there are marks for 3311, but no marks for 6441. Right, that's fine. You can kind of see that there's nothing there. However, if you want to make things a little bit more visible, you can use this function here, which will turn those nulls into marks. Oops. I still need to do that. Z equals. So we don't have a mark, it's going to display question mark rather than nothing. Hopefully this will work. One thing that's going to look a little bit strange, and I'll point that out after I run it. One thing that's going to look a little bit strange, what's the problem? Invert. Interesting. Wasn't expecting that to happen. And obviously can't convert that to integer. Let's try this. Try typecasting it. things a little bit tricky, so I'll just have to, I don't know, do something that's obviously not a real mark. So now we get something appearing in place of those nulls. So that's the point of coalesce. There may be other contexts where it's important that the null appears as something useful in the context of the application that you're dealing with. So, unless mark is not is a text value, this example here isn't going to work. Oh, I just thought of a way that I might be able to fudge it. Let's see, rather than casting to text afterwards, let's try doing it here. And then there you go. Right, so rather than having nothing appear, we get a question mark to indicate that the mark isn't there, done yet. Right, so what's interesting there, the use of coalesce to convert something that may or may not be null. If it's not null, it'll display the value. If it is null, it'll display some alternative value, which is that. Typecasting, I mentioned that last time, double colon introduces a typecast, and you can do reasonable kind of typecast, so you can cast numeric values to text. Other thing to notice, that what we get as the heading here is coalesce. Maybe we don't want that, and we can actually change that by adding another element to the output and say the actual name I want to be associated with that is the name mark. Now, Postgres isn't going to get confused about this mark and this mark, I hope. And so we'll change the column heading to now say mark rather than coalesce, which is not so clever or not so useful. So you can change the label that appears on the column by using as. We'll see that's used in other places as well. Alright, and as I say on the slide, nullif is sort of an inverse of coalesce. Another kind of conditional expression is case statement. Now, this is getting weirder and weirder, but for example, if I didn't store the grades in the table, but I wanted them to appear, then I could use a case statement to take each of the marks and convert it to a grade value. So the kind of thing that I'm saying here, case, if the mark is greater than or equal to 85, then the value that appears is HD, the value for the grade. So I need to add an extra column. Do I want to type all this in? No, I don't. So I'll let you go and play with that. So that's a way of taking a value for a particular column, if you like, and converting it to some other value. Alright, so let's get on to something more fun, SQL queries. So SQL query is composed of a sequence of clauses. I'm sure you've all seen select from where, but there's more that you can do. Group by, to collect bunches of tuples that have a common property and treat them as a group, and then do interesting things with the group. See some examples of that coming up. And you can also specify conditions on the whole group rather than on individual tuples. So the where clause is going to apply a test to each individual tuple. The having clause is going to apply a test to a whole group. So that's the syntax, and the result of a query is always a relation which is displayed as a table in Postgres. Even if the result is just a single value, it's going to be displayed as a table. So, because everything is a table in the relational model. Alright, so here's an example. So we want to get student ID, student name, and their average mark, right, based on their enrolments. And the way we do that is, first thing we have to do, we have to connect the student to their enrolment data. The reason we need to do that is some of the information that we want is in the student table, some of the information that we want is in the enrolments table. Okay, and here, right, these two things here, I've got the other syntax down below, basically doing a join of the two tables. So what we're looking for is a tuple in the S table and a tuple in the E table that both have the same student ID involved, which is going to connect a student to one of their enrolments. Alright, so having done that join, we're going to get a bunch of tuples that have a student ID, a student name, and a mark, right, if we're doing things that way. What we're interested in is grouping all those student tuples, so we want all of the tuples for one particular student, and then what we want to do is compute an average mark from that collection of tuples. So how do we get a group of tuples for one student? We use group by clause, which is what this is. So we're grouping by the student ID and the student name. The only reason we need to include the name down here, we could group by the student ID alone, but if we want to use name in the select clause, it also has to appear in the group by clause. That's something that people find a little bit weird up front, and surprisingly, SQLite allows you to omit the name. So you are doing a grouping based on the student ID, but you're collecting the name separately. So what we're doing here is we're collecting tuples that have the same student ID and the same student name into a group. Then each of those tuples happens to also have a mark attached to it after the join, and then we're taking the average of that. Unfortunately, I don't have a database. Oh, I guess I could add some students and then we can run this query. Let's go back into that database. We'll have to create another table of students, which I need to use the correct syntax for. Create a table of students, and all they're going to have is a student ID, which is an integer, and name, which is text. I'll do. Why didn't someone point that out before I ran? Notice this table has the same name as the database, doesn't matter, they're in separate namespaces if you like. Alright, so we need to add some students. Let's add 54321, so I'm using the student IDs up here. That's the one called John. And what else we got? 544. So what? 54333. Now, one thing I haven't done, I haven't said that the SID in the students table, or at least rather probably the other way around, I haven't said that the SID in the enrolments table has to refer to a valid student that exists in the students table. So if I wanted to I could leave out one of the students that's mentioned up here and not give them an entry in the students table, and Postgres wouldn't complain. Ideally, everyone who appears in the enrolments table should also appear in the students table, so I'll make sure they do. Alright, so now we've got 4 students, 5 enrolment entries. So if I do select start from enrolments, tab completion, I get that. If I do select start from students, I get that. And if I do select from students, and I think I might get away with this because the join fields have the same name. No, I won't. Alright. So we want the SID ID field in the students table to be the same as the SID value in the enrolments table. What do I do there? Oh, enrolments. And in fact, I would normally split this over 2 lines so we don't get things that are too long. Now, I'm saying students.sid, enrolments.sid, that gets a bit tedious if I have to keep typing students and enrolments everywhere. So I can actually, on the fly, define some shorthand and say, I'm going to use S when I mean students table, I'm going to use E when I mean enrolments table, and then I can do this. And then I don't have to remember that E is plural. Ooh, I don't like the way that E has been highlighted. That means it's a keyword. Some keywords you're allowed to use as identifiers, which is what I'm doing here. Other keywords you're not. So I think, I couldn't say students join enrolments, Anyway, hopefully this will work. Alright. So it gives me a table like that. Distinguishing feature of that is that on each line I've got a SID field, I've got 2 SID fields, but it's always going to have the same value. The 2 SID fields on each line, and that's what the join is doing for me. Alright, so that's all very nice. What I'm interested in is getting groups of students, or getting groups for each student. So I've kind of simulated that here. In fact, I had that already. So I've got a group here that's for that student, and all the other groups are a bit boring because I've only got 1 entry in them. But the group, I think, rather than doing order by, I can do group by facts. Let me use the editor, makes things easier. Right, so I've done the join. And if I knew how to use the editor, it would make life a lot easier. Alright, group by SID. So what I could do here is do something like this, which is going to tell me for each student how many enrolment entries they have, so it doesn't count. So the count applies to the group defined by a particular student ID. So there's going to be multiple tuples with a common student ID. All I'm doing is counting how many tuples there are. So let's have a look at that. So 55321 has 2 tuples, so they were enrolled in 2 courses. Everyone else was enrolled only in 1 course. Alright. Now that wasn't what I wanted. I actually wanted the average of their enrollment marks. Okay, and for the student who did one course and got a null for that course and didn't have a mark for that course would get a null. The other student who, so John had also done this course, didn't get a mark for it. So in computing the average, Postgres decides I'll just ignore something that's null. So I'll compute the average based on the known marks. It's not like I'm going to treat null as 0 or something. I just ignore it. But notice that it didn't ignore that line here because it knows the student has 2 enrolment records, regardless of whether there's a mark associated with enrolment. Alright, now what we wanted, we actually wanted to have the name. So let's try that for a start. This isn't going to work, but I wanted to show you if it does work. Good, it's not going to work. So that doesn't work because you can't have a value that's not included in the group by or is not included in an accumulation. So basically what you're doing for these group bys, you're forming a group and the intention is that for that group you want to compute some kind of summation of what's going on in the group. So computing an average of one column in the group, computing the count of the number of entries in the group, things like that. If you want to, but you can't include other attributes unless you're using SQLite. So if I actually wanted to do that, I'd need to include the name as part of the group by clause. So then Postgres knows, all right, I've got a group where we've got common student ID and student name, and they're allowed to be referenced in the select clause. So then we end up with something like that. Any questions on that? I'm going to do lots more SQL in the next hour or so. So hopefully those any kind of questions like that will be cleared up. So you can do joins in 2 different ways. That's the way I did it there, or something roughly like that. I happen to have different field names, but you can also do them like this, where you simply put a big list of tables and then you specify in the where clause what the join conditions are. Okay? Or you can say here I want to join these 2 tables and that's the join condition. So in the past I always used to do it this way, but recently I've started doing everything like this. I think that's probably better, but it's up to you. Alright, so I think we kind of looked at that, except the attribute names were different. This was called SID and that was also called SID, so that's fine. But I think, we didn't have grades either, we just had marks. Form groups of tuples that have common SID and name fields. For each group, compute an average mark and then form the result tuples. So there's a little bit going on there. Alright, so what we want to look at now is how do you solve problems in SQL. Problems are initiated with some kind of request, like give me a list of students and their marks, or give me the names of all the students in a particular course, or something like that. How many students failed the course, what's the highest mark, blah, blah, blah. So there's some request to get some information out of the database. In Postgres and all other relational databases, the result is going to be a table of some sort, containing at least one column and at least at least 0 tuples. So there may be no results for the query that you're looking for. So, maybe nobody failed 3311, and if you ask the query how many students failed, well, in that case you'll get a result of 0. If you asked, give me a list of all the students who failed. If no one failed, that list is going to be empty, so your table will have 0 tuples in it. Asking a question like, what's the highest mark? You're going to get a single tuple with the highest mark value because you're getting a single value, and it'll be a tuple in a table that has a single column, which might have the heading max or something like that. So I can do ask that query here, select max. And this is going to give me the maximum mark that anyone has ever achieved in a course in this database. So the highest mark overall is 80, but you can see that a column with a table with one column, and there's a single row in the result. And if you don't want to call, calling it max here kind of makes sense, but if you want it to be a bit more precise, you can do something like that. May give slightly more sensible column name. Who knows? All right. So before you can answer a query at all, you've got to know what the schema is like. So what information is stored in your database, and whereabouts is it stored? In other words, which tables is it stored in? How are the tables connected together? Because invariably, the information request that you get is going to require you to combine data from multiple tables. Okay? So you need to know how the tables link, you need to know what information is contained in each table. So someone's going to ask for marks, say, so you need to know what attributes in the schema store the marks or contain the marks. And then obviously you need to know which table that attribute lives in. You need to know how to combine the tables. So if you want marks that include a student name and a mark, the name is in one table, the mark is in another table, so you've got to get information from those two tables together, like we did in the previous example. You might want to, in fact, you invariably want to filter out stuff, so I'm only interested in students who scored high distinctions, so you'd use a where clause to restrict the results to just tuples satisfying that condition. If you need to group up the tuples in the result table, you can use group by to do that. And in the select clause, you can specify not just what attributes you want to appear in the result, and not just a different name for them using as, but you can also use arbitrary expressions combining the results, combining the values in the columns. Alright, so one final thing before we start solving queries on my favourite database is the notion of a view. So when you're writing programs, you don't just duplicate chunks of code unless you're in a big hurry. You tend to take the chunks of code and embed them in a function, and then you can just call the function with a single word. So similarly, SQL provides the notion of a view where you can take a query and you can give it a name, and then you can use that query later on simply by specifying the name. And the interesting thing about it is that the view kind of acts like a table. To all intents and purposes, it looks like a table. So you can use it in join operations, in future queries, and so on. So to create a view, use the create view keywords, give it a name, as, and optionally you can specify what the names of the attributes are. You can also specify what the names of the attributes are in the query. So every time you use the name of the view, it runs that query and gives you the result of that query. Okay. And in fact, a lot of the views in the catalog schema that Postgres provides, they kind of look like tables, but a lot of them are actually done as views. So sometimes it's a little bit hard to tell whether a given thing is a view or a real table. Of course, if you wrote the view, you'd know that. All right, so here's a simple database about beer. Beers have names, and they're made by brewers, which in this case are called manufacturers. There are people who drink beer, they have names, they have addresses, they have phone numbers. There are places where they drink beer, bars which have names and addresses and have some kind of license number. You can see that the primary keys in this database are all names. That simplifies a lot of the queries because you're getting the information that you want without having to go and do another join to extract it. So we saw in the student enrolment example, if we wanted the student's name, we had to join the enrolments table with the students table to get the name. In this case, we've got the name already as a primary key in the table, and it's also going to end up as a foreign key in this table. Well, it won't be because it's an end-to-end relationship, but the name is going to end up as a value in this table. So drinkers can like beers, beers can be liked by drinkers. I haven't bothered specifying participation constraints here. Bars sell beers, you could argue it's not much of a bar if it doesn't sell any beers. And beers can be sold in multiple bars. When a beer is sold somewhere, it's got a price, which is not uniform across every bar. Each bar decides on the price for particular beers. And drinkers go to bars to drink beers. And a drinker can go to multiple bars. Bars have multiple drinkers. Okay, so here's a bunch of questions. First thing to do, I said, a prerequisite is to know your schema. So, and in fact, the schema's right there. Although it's very small, is that legible? Just maybe. Right, so we said that ER diagram we've converted to a relational schema here. The end-to-end relationships end up as relations with a pair of foreign keys that links one entity from one table, like drinkers, to an entity in another table like beers, and that's how you implement the likes relationship. So you've got one table for each of the entities, the bars, drinkers and beers, and you've got one table for each of the relationships. And of course you can see that we've got an extra attribute in the sales relation to indicate the price. Alright, so if I wanted to find out what beers are made by Chewies, first thing I can look at is what beers do I actually have in the database. So there's a bunch of beers. Right? What beers are made by Chewies? So made by tells me I'm talking about the manufacturer, and so this is where you've got to interpret the information request. What beers are made by Chewies? Presumably I want the names of the beers, and the manufacturer, the person who makes the beers, has to be Chewies. So let's select the beer name from the beers table, where Chewies. And should complain. Alright, I'll just type it. What the hell's going on? It's giving me some weirdo prompt, and it hasn't actually run my query despite the fact that I put a semicolon at the end of the line.
You have to put 2 apostrophes.
Correct. Alright, So what's happened here is that's been treated as a single string. There's the character S floating around, who knows what that's doing. And then I started another string, which hasn't yet been terminated. So if I wanted to, I can stick a single quote there and then put a semicolon, and then it would complain that this S sitting between this string and this string is a little bit weird. So what I needed to do there was double up the quote. So that will escape that quote, and then it will print out the names of all the beers that TUI's manufactures. And of course, I mentioned the other day that we've got an alternative notation if you actually want to use escape sequences, because you think doubling up the quotes as a way of escaping it is a bit weird. Pretty sure this will also work. Yeah, so it does. Actually, it's a bit unfortunate that \E doesn't leave the query sitting there. So that was the query that I ran there. That's the query in more standard SQL syntax. Okay. Show beers. So I want to look at the beers table, and I've already done that. I just did so I can start from beers, and it says name Manf. And I don't like those labels. I'd rather have beer and brewer as the headings on those columns. So we've already seen how to do that using as. And if I actually want the column headings to have uppercase letters, I need to put it in double quotes. Name is beer. So they're not strings, they're names, and they're case, if you like, case-sensitive names, so the case is retained. So now we end up with that. If I hadn't put those quotes, it would have been lowercase b in both cases. How many different beers are there? That's pretty straightforward. I can simply count the number of entries in the beers table. So it's 26. How many brewers are there? And I guess what I could do is I could also have counted the number of names. Now, if there were two beers with the same name, and there don't happen to be in this case, they would you'd still get the result 26. If you wanted to get something different, if you wanted to just have the distinct beer names, you'd have to include the keyword distinct. And in fact, that's part of the next query, which is how many different brewers are there. So if I simply count the manufacturers, I'm going to get 26. That includes some repetition, so you can see Carlton appears multiple times, TUI appears a few times, James Squire appears a few times. Each of those has been counted in that count statement. If I only want the distinct ones, then the keyword distinct will do that for me. So there's actually only 12 different brewers, but there are 26 entries in the beers table, which is what that was counting. And if you want to just look at the brewers, you can do it like this. So they're all the different brewers. As you can see, there's no repetitions in that. Yeah.
Don't use group in this scenarios then?
You could use it if you wanted to do something like count how many beers each manufacturer made. If you just do, here we're trying to, what are we trying to do? We're trying to count the number of different manufacturers. I don't think group by this, not a notion of counting the number of groups. really. So that isn't going to help. One thing to notice, and this actually gives you a bit of a clue about how Postgres works internally, is if we look at the brewer names up here, pretty random order. If we look at them down here, they're not in they're not in order. I thought they would be. Maybe it's using hashing. All right. If I want them to be in order, what do? There's an order by clause, and I can do that. Should look closer. That's interesting. Things change with Postgres from version to version. In some of the older versions of Postgres, doing that would guarantee that things came out in sorted order. With the current version of Postgres, they don't. Which I guess is one reason why you need to be careful which version you're using. The argument that Postgres could make is, well, it's the same set of results. If you are particularly interested in having them in a certain order, that's your problem to organise by doing something like this. Alright, how many different brewers are there? Which beers does John like? This query ends up being a little bit easy. Well, let's first of all, so obviously we're interested in the likes table. We might want to use the right syntax. And we're interested in the drinker. Check that that's actually the name. So we've got a likes, drinker, and beer. Other fields where the drinker equals John. Okay, so there are all the beers that John likes. So like I said, we can do that in a single query because the values that we want are actually the foreign keys in that table. So which beers does John like? Alright, find brewers whose beers John likes. Now we need to connect the beer up to the beers table and then extract the brewer from that. So we are going to have to do a join for this. Alright, so from likes, given name, join beers B, and what we're joining them on is the beer that's mentioned in the likes table is the same one that's mentioned in the beers table. So sure, we've got a repetition of the beer name, but we don't care about that because what we're really interested in extracting is the manufacturer component there. So to do that, we simply get the manf component. Notice I haven't qualified manf there because there's only one manf. What's that? There's only one manf field in the system. Gosh, lost control of the eye. Alright, so that's the manufacturers of the beers that John likes. Of course, we've got repetitions, but we know how to deal with that. So we can do it that way. Right. So there the point was that we had to connect information from two different tables, and we do that using a join. Alright, find brewers whose beers John likes. Find pairs of beers by the same manufacturer. Interesting. Pairs of beers. Now that suggests that we're going to need a beer from the beers table and another beer from the beers table. And how do we do that in a single query? Well, the other thing was that they're from the same manufacturer. So if we had a copy of the beers table here and another copy of the beers table here, and we did a join on the manufacturer, we would at least get pairs of beers from the same manufacturer. So let's start with that. Now the question is, how do we get beers table and beers table? And the trick is you just give them different names. And it's perfectly possible to join a table with itself. And what are we joining on? We're joining on the manufacturer. So it's going to give us a lot more information than we want. What we're really interested in was the beer names. So we need to start getting rid of some of the columns. So P1 dot name. So here we need to distinguish those two names. You can't just write name, otherwise Postgres will complain that it's ambiguous. Which name do you mean? So you need to qualify and say the first name comes from the version of the table that I've decided to call V1. The second name comes from the version of the table that I've decided to call B2. Alright, so now we get something like this. And I guess if you really wanted proof, you get at the manufacturer in just to make sure they came from the same brewer. Alright, one small issue is that we get pairs that have the same beer paired with itself. That's potentially not that interesting, and also we end up with beers. Let's see if I can see some examples. Yes, I can. So here we've got the pair Crown Lager and Foster's Lager, and here we've got Foster's Lager and Crown Lager. So maybe we don't want all of that duplication happening in the table. How can we get rid of it? And we can't just use distinct, because those two tuples there are distinct. They've got the same, they happen to have the same pair of names, but they're in a different order. That makes them different tuples. Any suggestions? It's going to sound good on the recording. Well, the trick here is that we want to eliminate duplicate pairs. So, what we can do is to trick the system by saying I'm only interested in the pair where the first beer has a name which is smaller than the name in the second beer. So we can use conditions. So that'll mean we don't get Crown Lager and Foster's and Crown Lager. We simply get the first one of those two, because Crown Lager is less than Foster's. So that's got a lot less. I didn't actually show all of the tuples in the last one, but it would have had a lot more than 26. Anyone see a problem? I see a problem. If we go back to the example before that, which I think was that, what happened to this beer? It's gone. Do we probably want that? Oh, this is actually trickier than I thought. It's not really, no, it's not a pair of beers from the same manufacturer, it's the same beer from the same manufacturer, so it doesn't matter that it doesn't appear in the result. But just to point out that those instances are going to go away. So you can see for every beer we're going to have an instance where we pair the beer with itself. Same here. So we've got rid of all of those, and we've also got rid of the duplicates, conceptual duplicates where we've got A and B and B and A. So we're only interested in having one of those, so we take A and B. Alright, that looks like the end of the first hour, so let's